Hi, Ira. In this session, I will be hosting, and Andrea will be hosting. Can you hear me? Okay, it seems that you are not co-host yet. You are.
Yeah, I am.
Maybe we can wait still 1 minute because I see that the number of participants is still increasing.
Okay.
Quite a bit. All right, are you ready?
Yeah.
Okay, perfect. Maybe we can start the recording then. If the assistants, maybe I can do it myself. No. Hi, ICTS assistants. Maybe you could start the recording now.
Yes, I'm here. Sorry.
No problem.
I couldn't hear you. So, can you repeat?
Yeah, we're going to start now. So the recording,
yes.
Perfect.
You can start.
Okay. All right. All right. So we are very happy to have Ira, who will be delivering the third lecture on gravitational waves from the early universe. On effective field theory for gravitational waves. Please.
Okay, thank you. Okay, so let's pick up where we left off last time. We were discussing power, or the power radiated in a QED binary. And just to remind you of the logical flow, we started by calculating in the full theory, for the exact theory. Because QED is Gaussian, we could solve it exactly. And if you remember, and we were able to calculate J exactly, W of J. Where this was the Feynman propagator. And then we interpreted the real part of E as a set of potentials in the non-relativistic approximation. And the imaginary part was proportional to the width. And this allowed us to calculate the power. Okay, so we finished off by showing that the power loss was proportional to this over some time period, was proportional to the second derivative of the dipole moment, where P was the dipole moment of the binary system itself. Right, so essentially we have some orbit, and then it forms some effective particles with dipole moment. This has some dipole moment, and the rate of change of that dipole moment gives you the power loss. So this was all done in the full theory, and in the full theory, we were able to discern that the potentials were due to a photon which had a propagator look like this, and we called this was the 2-point function of the potential propagator, and we said that AP has momenta k mu that scale as v over r and r, and we said that the radiation, I think we used dotted lines for the potential, and the radiation was real in the sense that it was on shell, and for the radiation field, we said K goes like V over R, and all the components are small compared to R due to the V suppression, okay? And then we use this to build the EFT. Where now L was a function of x dot, a potential, and a radiation, okay? And then we integrated out the potential to yield some action that only depended on the radiation field, and the positions where this included the dependence on the leading order Coulomb potential, and then we had the subleading order V squared potential, which depended on X and V, okay? And now what we'd like to do is to figure out how to calculate the power loss in the effective theory. So in the full theory, we just did it because we could solve it. But in general, as we said before, when we get to GR, that won't be possible anymore. So what we'd like to do is be able to calculate the power loss in the effective theory, okay? So if you remember, we said the prime directive of the effective theory is that every term scale homogeneously. In V, which we accomplished. And the other, the secondary directive is that all terms must obey the symmetry. It must be invariant under the symmetries. Okay. Now, in our case, we've broken Lorentz invariance by taking the non-relativistic limit, but we should still have gauge invariance. Okay. So our effective theory should still be gauge invariant. So let's remind ourselves what our effective theory looks like. So we have S. We still have our kinetic term, which we haven't expanded out in V yet, but it's relatively easy to do that. I should say my notation is always eta mu nu is 1 minus 1 minus 1. Okay, so this is the kinetic term. So if we expand that out, we're going to get, so there's a sum over I here for each world line. We're going to get sum over I 1/2 mvi squared plus relativistic corrections to that. And then we have minus the potentials. which we calculated last time. And then we still have J mu A mu R. Remember J mu there's a sum over I for all the particles. Okay, and there's a charge for each particle. Good. Now, we said that we have to, every term must scale homogeneously. Okay, and at this point, these terms we know scale homogeneously, and we could certainly expand this so each term scales homogeneously, but what about this guy? Okay, so we said that the wavelength of the radiation, so K radiation goes like V over R, which is much, much greater than 1 over R. Okay, so our dipole expansion tells us that this has to be much less than 1. Right? So we have to multiple expand. So this is of order V. So instead of just inequality, let me say this thing's order V. So we must multiple expand the radiation field. That is forced upon us by the prime directive. Okay, so we're going to write J mu A mu radiation. So this becomes sum over I EI V mu. I'm going to suppress the time argument now because just to save space. Okay, so this is, notice now this field, because of the delta function here, there's still an integral over dt, which I've taken to be my affine parameter to be dt. Okay, so now this field here is evaluated on the world line. Okay, but now we're forced to multiple expand this. So let's write this out. So we have dt sum over I EI. Let's write it first. So we have V0 I A0 minus V I AI. Okay, and our multiple expansion is going to lead to oops, sorry. Okay, so notice I've only kept up to order v squared. So let's see if we can simplify this. Now the final result is supposed to look gauge invariant, right? So we need some coupling that when we're done is going to look gauge invariant. So we better be able to write this in a gauge invariant form. Okay, so the first term, remember this guy is 1 with our affine parameterization. So we have the first term is dt A0 Q total. That's the coupling of A0 to the total charge. And then we have another term. So in this term, let me integrate this term by parts. So then I have plus x dot ai dot 0t minus v. Sorry, I'm missing a. Oh no, that. Well, I'm missing an index here. This should not be here. Sorry. Right, that comes from the expansion of this term. Minus x dot grad A0 0t plus dot 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 dot. Okay, but these two terms, remember that EI is D0 AI minus DI A0. So this second term just gives me sum over I xi EI dotted into E 0 and t. And this is nothing but P dot E. Okay, so we end up, E of course is gauge invariant. So our effective action, S effective, is Q A0 of 0 and t plus P dot E of 0 and t. And so why is this gauge invariant? The first term does not look gauge invariant. However, A0 goes to A0 plus D0 chi under a gauge transformation. And since Q is a conserved quantity, therefore it's a total derivative and we can drop it. Okay, so we end up with an action which is explicitly gauge invariant. And if you wish, you could carry out this expansion further and you would get the quadrupole dotted into the first derivative of the electric field, and you get the magnetic dipole and so forth and so on. And you're assured you'll get a gauge invariant result because we've worked in the background field gauge. Even if you calculated quantum corrections, you would still get a gauge invariant result. But of course, everything we're doing here is classical. Sorry about that. Okay, so good. So now we have our effective theory. So what is our effective theory? So we have sum over I, 1/2 mi vi squared minus v of xi and xi dot, which we calculated, plus q A0 and these guys all get integrated. So notice that here, I should put a dt, and these fields all depend on t. Okay. And now, and remember, this is composed of the radiation field. And we can power count each one of these terms as we did before. And this would be leading order, this would be order v, and so forth and so on. Sorry, v squared, no v, sorry, v squared, v squared. And now we can calculate anything we want. So remember the algorithm is, so remember these p's contain our functions of the xi's. So in order to calculate the power loss, we first have to calculate the equations of motion for the xi's, solve them, and plug them into these p's, okay? So let's calculate the power loss. Well, how do we calculate the power loss? We know how to do that. We calculate the probability to emit one photon. We square it. And that will give us the probability to emit one photon. So what we're going to do is we're going to integrate this thing weighted by the energy. And this is going to be the power loss, okay? So another way of saying this is this thing is proportional to the imaginary part of this Feynman diagram. And the reason I want to write it like this is because it's going to look exactly like the calculation that we did before, right? So so here, these are each insertions of P dot E, right? So if we look at this, this amplitude that we're going to take the imaginary part of, so we're going to have two insertions of P dot E. So we're going to have a dt prime, P of E at T, P dot E T prime, okay? And just using standard Feynman technology, we get one Wick contraction between these two electric fields. So if we open this up, so this P depends on T. And then this P depends on T prime. Okay. And if we use Feynman gauge, remember the Feynman gauge propagator is proportional to G mu nu. So which is to say that the contraction, the Wick contraction of two A's, like this. So there'll be a Wick contraction between these two terms, and there'll be a Wick contraction between these two terms, but no cross terms. And then if the propagator, of course, will go like k squared plus I epsilon. And then if we take the imaginary part, this is going to give us our delta function, right? So there's a d4k, which leads to d3k once we use the delta function. And then we could calculate these Wick contractions and just do the algebra, and you're going to get P of T dot P of T prime e to the minus I k t. Okay, so this is the imaginary part of M. And remember, P, we need to weight the integral by the energy. So I'm going to get another factor of the energy here. With this integral. Well, that happens sometimes. Okay, let me just do this. And then, of course, you can do these integrals and you just end up with dt, time left integral left over, and p. Okay. That's exactly what we got classically. All right. So let me pause now for questions. So this is a logical stopping point. So what we've just done is we've re-derived the expansion of the exact result by first taking the effective theory and then calculating it within the effective theory for the purposes of the next step. Or we're talking about one other small thing before we move on to GR. So let me pause here for questions.
Sounds good. So there's a question by Max.
Hi. Could you please comment a little bit on, so if we would now go to quantum theory, where exactly would this previous story change?
So that's right. So so notice that we've taken the so we're ignoring we're essentially ignoring finite mass effects, right? So our sources are like taking the electron mass to infinity, right? So in fact, so maybe this is a good point to discuss this. We've been drawing Feynman diagrams with these lines here, right? And so for instance, our potential we drew was like that. But that's a little bit misleading because this implies that the sources are propagating, that they have propagators. But we're treating the sources as classical objects. So a more correct diagram would just be this, where these are just insertions of classical sources, right? So the difference between a quantum source and a classical source is a quantum source, of course, has some propagator that looks like this. But a classical source actually has a propagator that looks like this, where v is the velocity. So what we're doing is we're assuming basically when we look at these exchanges that there's no quantum fluctuations in the lines, okay? Now, where would the first quantum correction come from? And that's because we're considering, very massive objects. Because in the end, that's what we're interested in, right? We're not going to try to do small black holes. We're going to try to do astrophysical black holes. We can't do small black holes because no one knows how to do that. Where by small I mean on the order of the Planck mass, the Schwarzschild radius. Of course, you would have quantum corrections coming from electrons that would correct the Coulomb law. So for instance, you would have an electron loop here. And the net effect of those electron loops will be to take every E and replace it by E of R, right? So that says these are going to give logarithms of R. Well, not, in X space, will give you logarithms of R. And so E of R will just be the running, where E of R is the running coupling. And in QED, that's really the only correction. Of course, I mean, you'd have to calculate, if to all orders in quantum corrections, you would need to include all the corrections to this. But that's the only, if you knew the self-energy of the photon, you would be done, right? Now, of course, at distances long compared to the electron mass, these effects are all suppressed, right? So from the point of view of effective field theory for R much greater than 1 over ME, the coupling just freezes, right? The coupling stops to run because at these long distances, you really, the any effect of a massive particle is going to be suppressed by the mass, right? So the corrections will be down by RME. Yeah. So in any classical problem, all those quantum corrections just get absorbed into defining alpha at infinity, at r equal infinity, essentially, which is 1 over 137, right? If you start to probe distances on the order of the electron mass, then these will be corrected by logs of r, right? But these guys are going to be down by RME. Did that answer the question?
Yes. I see. Thank you very much.
Okay, so before we go to GR, I can't resist, especially since this is a particle physics summer school and not necessarily a GR summer school. I wanted to show you how you could use these results in QED to learn something interesting. Okay, so let's talk about finite size effects. So what are the first finite size effects in electrodynamics? Well, there's terms that go, we said, like F squared. And I'm not going to worry about the RPI for the moment and putting in the square root of V's. So this is what the finite size action looks like. Okay. So what are these finite size effects? Well, first let me rewrite them as CE times E squared plus CB times B squared, where you can work out that CE is minus 2 C1 plus C2, and CB is minus 2 C2. So remember, F squared is just some combination of E squared and B squared, and V dot F also can be written in that way, can be decomposed in terms of E and B. Okay, so how would we fix these coefficients? These are some unknowns. Well, we'd have to do some matching procedure. So we fix CE and CB by what's known as a matching procedure. Okay, so how do we do that? So let's take an example. Suppose we had a spherical conducting shell, and we wanted to determine what are the values of CE and CB for that conducting shell. Okay, so the idea is the following. So we solve the full theory, and then we match onto effective theory to determine the C's. Right? So what do I mean by that? So we're free to match anything we wish, any observable that we want, which is to say, whatever observable you take in the effective theory should match the full theory. So, and once you match those coefficients, you're done. You can use them for any process. So you can take one physical process, match for the C's, and then use the effective theory in any physical process you want, because once you know C, you're done. The game is over. So it's easiest, you should always choose to match using the simplest possible observable. So what we'll do is we'll place the sphere in some dipole field, in some background field, and then we'll ask for the response. Okay, so we're gonna write A mu as A mu background plus delta A mu. Okay, And we're going to calculate this delta A mu. So what we do is we take our finite size action. So we take S finite size. And now we're going to write it as E or delta E. E background plus delta E squared. Let me just do the CE piece in this way. Okay. And we're going to calculate to linear order in delta E. So this is going to give E background squared plus E background dot delta E background. Plus the pieces we're interested in. Okay. So in the effective theory, we can calculate delta E. So this E background is acting like a source is equivalent to some J. So this is just like J dot E. And so I know how to calculate delta E. It's just going to be the convolution of the Green's function where now this is E. Right? That's how you solve the boundary value problem in electrodynamics. So in the notes, I'm not going to go through the details, but sorry, that's not just, there's no delta E back, just delta E. So this field is going to take the form at long distances of, there's going to be some dipole field. An electric and magnetic dipole field at long distances. Okay. And then we can just read off the induced, so this is the induced dipole moment. This is the induced magnetic moment. Okay. So I can do this calculation as a function of E background, right? So that the induced dipole moments will be functions of the background, right? So now we know this is E background. So this comes out of the calculation. I haven't shown this. And so now all I have to do is solve the full theory. So I can go to Jackson and solve the boundary value problem for a sphere in a background field, and it goes like this. So this allows me to, this tells me that CE must be minus R cubed over 2. Okay, and I could do the same thing with CB. So this procedure of matching is a bread and butter calculation of any effective field theory. Okay, assuming that you can calculate in the full theory. So in a counterexample that would be the chiral Lagrangian in QCD. And there, the coefficients we can't match because we don't know the full theory. So the only way we can fix those coefficients, well, we know the full theory, but we don't know how to calculate analytically, at least. So in that case, the coefficients have to be fixed from experiment. So you take some observable, you use these operators to calculate the prediction for that observable in terms of the coefficients. You measure it in an experiment, and then you extract the value of C. In this case, which is such a useful pedagogical example, you can calculate the full theory. It's just a Jackson problem. Put a charged sphere in a background electric field, calculate how it deforms, right? Do the same thing in the effective theory, which is what we've done here, and then match the two, and that allows you to just extract the value of CE. And if you did in the notes, I show also that CB can also be extracted and only differs by a factor of 2. Okay, so what use would these finite size effects, what use are they? And now I'm going to show you, before we go back to gravity waves, how you can do some interesting molecular physics using this result. So let me consider 2 neutral molecules, okay? And their distance r is much greater than this r. So our effective theory should apply. And I asked, well, what's the force on these 2 molecules? Okay, so our action now, each one of these molecules could be different. So I'm going to give each one of them a different polarizability. So these C's are, you can see from this definition, the C's are proportional to alpha. This is the usual nomenclature for polarizability. Okay, so in principle, these could be 2 different types of molecules. It doesn't matter. And we could ask, well, what is the force between these 2 guys? Well, we know how to calculate potentials in our effective theory. So at our disposal, we only have these terms because these are, so Q is 0. So there's no P and P is 0. So there's no P dot E, there's no nothing. There's the only interactions are due to the polarizabilities. So what can happen is that what's the first contribution to the potential? Okay, well, from Feynman diagramology, we know we have 2 lines coming off, right? Because it's quadratic and E squared. And now I have to contract the lines in some way. And that's all we can do. Okay. So we can calculate this diagram, but before we do that, let's just, the power of this formalism is manifest by the fact that even without doing a calculation, we can determine how the force depends on R for 2 neutral molecules. Well, because we know it goes like CE, CE, so V of R is going to go like CE squared. And then there's going to be R to some power here. Okay, it's going to be some power law force. But we know that CE goes like R cubed, just on dimensional ground. So even if we didn't do the matching, we would still know that CE goes like R cubed. Why is that? Well, from reasoning in effective field theory, right? We know that the small expansion parameter is R over R. Right, that's our starting point. So remember, we had 2 expansion parameters. In the first place, we took the finite size object and we shrunk it to a point, and that gave us an R over R expansion. And then we did the small v expansion, and if we drop the finite size, then that would mean we'd only be working to leading order in little r over big R. Keeping the first finite size effects are the first corrections in little r over big R. So these guys have to scale with some power of R, because that's our expansion parameter, small, big R. But just on dimensional grounds, so this has a dt here, and in our units where h bar equals c equals 1, everything has energy scaling. F scales like energy squared. Sorry, energy is, let me use mass so we don't get confused with electric fields, right? And then we have a dt that scales like 1 over mass. So that must mean, oops, I've got too many dt's, sorry. So this is mass to the 4th. So this has to scale like mass to the -3, which is r cubed, since r scales with 1 over mass. So even if we had not done the matching, we know exactly how the c's scale with r. Okay. So now, even if we didn't know anything about how to do these calculations, all we need to know is that 2 insertions of C is all we need to get a force, because now we know this thing goes like R cubed squared. And then to have the units of energy, it has to go like R to the 7. Okay? So we've just determined that V of R goes like CE squared over R to the 7th. And that's pretty cool because there's been no physical input whatsoever, right? This was just purely based on dimensional analysis and power counting, okay? And the basic assumptions of effective field theory. This is known as the Casimir-Poldar force. And in the notes, I show you how to calculate the coefficient here by calculating this diagram. Now, this may puzzle you a little bit because normally when you learn atomic physics, quantum mechanics, if you take a class in quantum mechanics, you find that the first force between neutral atoms is the van der Waals force. And that potentially goes like 1 over R to the 6th. So what's going on here? And the answer is, so the question is to, how much can we trust this result? Well, these guys are atoms and they have some excitations. And so we're ignoring all those excitations. So in the language of effective field theory, we've integrated out all the excited states. So it better be that we can't excite those excited states in our problem, right? But if we bring these guys close enough together, then the typical wavelength of these potential modes we know goes like K will be 1 over R, right? And if the energy carried by this photon is of order the first excited state, then this theory will break down, and then you'll need to include the excitations of the atom. And when you do that, you'll get the R to the 6th. And this is actually, I actually derived that in the notes for those of you who are interested. And sort of the cool thing about this whole program, which has never really been explored, is you could start to look at nonlinear effects. So for instance, the prime directive tells us that we could also have terms like e to the 4th, right, which will be higher order in, let's call it E4, which will be higher order. And these will lead to some interesting nonlinear effects, because you could draw diagrams like this, right? And I don't know, what's been calculated and what hasn't in atomic physics, but it would be fun to explore what the effective theory can tell you about, say, nonlinear optics and things like that. But that, as far as I know, no one has looked at that. Okay, so this is a good point to stop in this lecture. And let's take a break, and then when we come back, we will start on relativity, on GR. Are there any questions at this point?
Sounds good. What about we take the questions in 5 minutes after the break?
Sure.
So we leave 5 minutes to think about it, and maybe there will be more questions.
Sounds good.
Okay, see you in 5 minutes then.
Yep.
Right. Could you remind me, how should I pronounce your first name, Ira or Ira? Because,
Ira.
okay, sorry, because before I think
It's okay.
All right.
No problem.
Okay, so there's a question by Prisco.
Yeah, this probably relates to a question I asked on the first day. But so we calculated the coefficients for spherical objects. Do they change if we drop the spherical assumption? Because then, no,
yeah.
I mean, just, okay. But
yeah,
by how much? Yeah, that's also.
Yeah, so let me show you what happens if it's not spherical anymore. Can you see my screen? Can you see my screen?
Yes.
Okay. I saw in the chat that there seems to be a problem with lag. Is that still happening?
Yeah, a little bit, I think.
Was it like that yesterday too, or is it just today?
I think only today.
Oh, then I don't know what's going on. I'm sorry about that. So if you don't have spherical symmetry, then there's a preferred direction, and we have to change the action. So it's not just that the coefficients change, but now we have new terms in the action, right? So in particular, if the object has some breaking of spherical symmetry, then the object will have a permanent dipole moment, right? So now I can add terms to the action that look like this. Now remember, we don't get confused between the point particle action and the point particle, the binary. So remember what the logic was. It went like this, right? And then like this. So we start off with two finite size objects. We reduce it to an action for 2 point particles. Then when we multipole expanded, we left with 1 over p dot e, where this p is the p of the total system. Okay. Now, here, we assumed that there was no p dot e. In other words, the individual particles didn't have any multipole moments, right? So if the individual particles were oblong, then remember this action was just j mu a mu, right? But if this guy had spherical, something which broke spherical symmetry, I'd have to add more terms which knew about that preferred direction, which we haven't included, right? So, and in fact, you could show that by gauge invariance, you would have to generate a p dot e term where p was proportional to the permanent moment, right? And then if you had other moments, if you had some really complicated object, I don't know why it's doing that. That's weird. Sorry. If you had some complicated object with some weird shape, then this would have all sorts of multiple moments, and you'd have to include all of them. Sorry, something's wrong with my iPad. You'd have to include all of them to include those effects, right? Did that make sense?
Yeah, a lot.
Okay.
I just don't see, like, looking at the final thing we want to achieve, is this a problem? Like, will this be a problem that we have to kind of know the object in advance?
Absolutely, yes. So in general, if you don't know what the object is, you have to include all those terms, right? And in fact, we'll talk about what happens. For instance, what if the object is spinning, right? Then we're going to have to include those terms as well. So you can imagine how complicated it gets, right? Because in principle, in fact, the dipole moment could start to change with time, and it gets more complicated. So we've just taken the simplest example of a spherical object. And for LIGO, for instance, that's an excellent approximation because black holes and neutron stars are spherically symmetric. When they start to spin, of course, then they're no longer spherically symmetric. So we'll have to, if we have time tomorrow, we'll talk about spin and how to include it. So that may partially answer your question.
Yeah, that makes a lot of sense. So I'll just wait and see if tomorrow it's clear also.
Okay.
Thanks.
All right. Next question is by Mehmet.
Hello. I was curious about one statement that was in my head. It is to confirm. I'm asking now. Can I say that what we are doing right now is a kind of an Euler-Heisenberg Lagrangian supplemented with the information of how a classical source inserted in this Lagrangian?
So the Euler-Heisenberg Lagrangian is purely quantum mechanical.
Mhm.
The ideas behind it, of course, are very similar in the sense that so in Euler-Heisenberg, you at distances long compared to the electron mass, you integrate out the electron. So in the full theory, you would have this, and this would match onto a theory that went like f to the fourth, right? So it is certainly similar, but this is purely a quantum mechanical effect. Whereas so far we have not included anything quantum mechanical, but in spirit, it's similar, yeah. So Euler-Heisenberg was one of the first sort of effective field theories that was ever written down. Of course, for them, it was just sort of a model. They didn't really have control of anything, but the ideas were all there.
I see. But if I see the diagrams we draw up to now, these closed loops of photons, can I say that they are quantum effects as well?
Yeah, so good. So we'll talk about that within the context of GR. So certainly in QED, this would certainly be a quantum effect, right?
Mhm.
We'll see, for instance, in GR that there'll be potentials that look like this because GR is nonlinear. And that looks like a loop, but it's really not a loop. But we'll talk about that. We should really think about this as a diagram that looks like this with no loops. Okay, so we will talk about what's quantum and what's not quantum in the context of GR in just a few minutes.
Okay, but up to now, I can still think that we are in the classical realm.
Totally
okay.
classical, yeah.
Okay.
And will remain classical. The only thing I ever drew which wasn't classical was this, the Casimir-Poldar force. That's quantum mechanical.
Okay. And it's because how you resolve that effective vertex, like if it's
Yeah, this loop right here, any closed loop that doesn't involve an intermediate classical line will be quantum. So for instance, that's quantum. This is classical because this line isn't really there, right? This should better off be drawn like this, right? But notice that here, there's still a loop, even if I draw those lines as classical sources like that. So this is quantum, and this is not quantum. This is classical.
Okay. Thank you very much.
All right. Next question is by Max.
So since you brought up the Casimir-Poldar force, I was curious. So could you in this formalism also include like finite temperature effects?
Absolutely, sure, yeah. So the only difference is you need to include finite temperature propagators for the photons, and then the calculation would go through exactly the same. You could get the finite temperature force as well.
Oh, okay. Nice. Okay, thank you.
Mm-hmm. Okay. So let's press on to GR. So now let's do GR. But before we do that, we need to do one little piece of housekeeping that is important when building any effective field theory. And that is the fact that you can use the equations of motion, use of the equations of motion at the level of the action is allowed. And that's important because remember the algorithm is you write down every term in the action which is allowed by the symmetries, but some of them you can just eliminate. So any term in the action which vanishes using the equations of motion can be thrown away, which, as I mentioned in the first lecture, is a little bit counterintuitive quantum mechanically, because quantum mechanically, we know we have virtual particles which don't obey the equations of motion, right? Off-shell modes. So why are you allowed to use the equations of motion at the level of the action? Because the action is some off-shell quantity. It induces virtual effects. And the answer is there's something called the equivalence theorem, which is not the equivalence theorem of GR, but the equivalence theorem of quantum field theory, which states that any physical observable, then in particular the S matrix, is invariant under canonical field redefinitions. And that's going to allow us to use the equations of motion to eliminate any term in the action that vanishes by the equations of motion. So let me give you an example. So suppose I have a scalar field theory that looks something like this. Okay, so I'm making it as simple as possible. I've made a massless scalar field, and the equations of motion are, the leading order equations of motion are box phi is equal to 0. Now I have some operator here, and this operator will be, say, suppressed by some mass scale. So this is a higher dimensional operator. So C is going to go like some power of 1 over m, where this n is fixed by whatever the units of f are. So f is some polynomial in the field. If I knew the power, then I could choose m to give me the right answer. And if we're looking at energies much, much less than m, then this operator will be suppressed. So this would be an analog to one of our operators that, you know, like our E squared operator, something like that. Although E squared doesn't vanish by the equations of motion, but I can imagine, say, here is a good example. I could write down a term that went like d mu f mu nu squared. Okay, that would vanish by the equations of motion. This f here is not f mu nu. This is just some function of the field. So let me make a redefinition. Phi goes to phi minus c times f of phi. Okay, and then let me plug it into the action. So now L becomes phi minus c f of phi box phi minus c f of phi plus c box phi f of phi plus order c squared. Okay. So so this is gonna give us back phi box phi minus c f of phi box phi plus c box phi f plus order c squared. Okay. I've eliminated it from the action up to corrections of order c squared. But remember, if I'm calculating in a systematic way and I'm only calculating up to order c, I don't care about the c squared terms, right? So any operator which vanishes by the equations of motion can be eliminated up to subleading pieces. And if you're calculating to higher orders, you'd have to include those pieces. Okay? And so why are physical observables independent of these field redefinitions? And the answer is because remember that when we do a path integral, this is just a dummy variable. And it's not as if we have to worry about the boundary conditions on these fields. We take them off to infinity, right? So there's no boundary conditions. So I can make any field redefinition I want as long as the Jacobian is trivial. And so as long as I have a redefinition of this form, then everything just goes through and it allows me to eliminate all terms in the action which vanish by the equations of motion. So this is a very important result in field theory in general, but especially in effective field theory, because it allows you to make your life a lot easier by not having to write down terms in the action which vanish by the equations of motion. So that reduces the calculational burden in any effective field theory that you're working in. Okay. Are there any questions about that?
There's one by Max.
Yeah, sorry. Could you please explain why we can make use of this in the case of GR, but not in the electromagnetic case?
Oh no, you can use it in the electromagnetic case. It's just that I did. So for instance, in the electromagnetic case, we might have thought that we could write down a term like this, right? But that's zero by the equations of motion, so we don't have to include it.
Okay. Okay, thank you.
Yeah.
All right. Next question is by Basha.
Hi, so if a Jacobian is not trivial, probably we will have something like ghosts, and can we still use the definition in this case?
Yeah, so if you have a non-trivial, if it's a non-canonical transformation, you can get ghosts, and then you have to be very careful. So there's been work on this. The question is, can you make the ghosts decouple? It gets a little bit tricky.
Is it not heavy? Like ghosts are not heavy in this case?
So not necessarily, but if you want, on the Slack channel, I'll put a reference to a paper which discusses this issue.
Okay, it would be very good.
Okay.
Thank you.
Yeah.
Thank you.
Okay, so let's talk about GR now, and let's apply our algorithm to GR. So the first thing we need to do is we need to understand our power counting parameters. So that's the first order of business whenever you build an effective theory. Okay. Now GR is more complicated because we have more dimensional quantities. So we have R, we have M, and we have G Newton, right? And from our first lecture, we talked about the fact that as V goes to 0, we approach flat space. So it makes sense for us to expand around flat space. So we're going to use V as our expansion parameter, and we need to figure out how everyone else scales with V. So one way of doing that is just to remember that if we have a bound state, then we have a balance between the kinetic energy and the potential energy. This is also called the virial theorem. So this is only true for bound states. So we're crafting our effective theory to describe bound states. And that's crucial in the sense that we're using this relation, which is only true in certain kinematic configurations. So our theory will be limited to those configurations. Of course, those are the configurations that we're interested in. So we see that V squared scales as GM over R. Okay? And we're going to take that to be much less than 1. Now, we have another expansion parameter, that's going to allow us to differentiate between quantum and classical, right? So in particular, we're going to have an expansion parameter that goes like h bar over L. That's pretty small, right? For a classical orbit, that's an excellent approximation to drop that. So we know that L goes like R M V, right? And we just said that R goes like GM over V squared. So L goes like M, let's see, did I do that right? R goes like GM over V squared. So GM squared over V, which I'm going to write as M squared over M Planck squared 1 over V. So M squared over M Planck squared is going to go like V times L. So let me remind you that G Newton goes like 1 over 32 pi M Planck squared. Okay, so usually in GR, you'll never see M Planck because you need an H bar to go from M Planck to G Newton. But as particle physicists, we're usually trained to think about M Plancks and not G Newtons. Okay, so so our two expansion parameters are going to be V and 1 over L. So we're going to do a double expansion. So how should things, so the leading order action, S, well, S has the units of angular momentum, so the leading order action should scale as L, and then V to the 0. So every term in our action should be a sum of terms, each one that scales as L to the alpha, V to the beta. Okay, so it's a sum of terms. Let's call them operators, EI. Okay, and we're going to, in the end, we're going to drop any term that goes like, any terms in the action that don't scale like L. There'll be some terms that scale like 1 over L, and these will be quantum. Okay. So now we do exactly what we did in the case of electrodynamics. And we start off with our, so the first thing we're going to do is start off with a point particle action. So step 1 is to write down the point particle actions. Okay. So we know how to do that. That's minus mi. Okay. Now notice here, now we're doing GR, so we can't just take that to be flat space. And then we have the bulk action. Okay, and let me put in the canonical normalization. Okay, and then plus finite size terms, which we'll get to in a second. Okay. All right, now since we're expanding around flat space, the V equals 0 limit, we're going to write G mu nu as equal to eta mu nu plus h mu nu over m Planck plus h bar mu nu over m Planck. This will be the potential mode. And this will be the radiation mode. Okay, just like we did in electrodynamics. Okay, so now let's expand it out. So let's take our square root and we're going to take sorry, at this point this is still d lambda, and there should be a d lambda I here for each guy. And now we're going to take our affine parameter to be t. So now the kinetic term so I'm going to contract it with this is the contraction with this guy, and then we have plus okay. So now we can expand out the action in the fields, and so this thing is going to look like, just to give you a sample of what it looks like, rather ugly mess. Excuse me?
I passed your question by Max.
Oh, okay, yeah.
Yeah, so I would like to ask you about this expansion of G mu. So in the case of Maxwell, I was thinking of this potential mode as just having 1 degree of freedom. But now here in the gravity case, I would think that so at least in the relativistic case, the potential mode should have more than 1 degree of freedom, right? I guess that in the non-relativistic case, you really only end up with this thing, which is basically the Newton potential, or is this the wrong thinking?
I'm not exactly sure what you mean, but so the potential mode isn't really a dynamical degree of freedom, right? In the sense that at leading order, its propagator doesn't know about any time dependence, right?
Right.
So
right.
you can think of it more of as an auxiliary field that
Right.
we're going to solve for and remove from the theory. The radiation mode will have 2 degrees of freedom, the usual 2 transverse degrees of freedom of the graviton. I don't know if that addressed the question. I wasn't quite sure I understood the question.
Yes. I mean, I don't see what you mean, but I mean, in the Maxwell case, yes. I thought this longitudinal mode is really a non-propagating degree of freedom. So in the sense that you really have a function, but this function that doesn't obey equations of motions. But in the GR case, I thought that there are more than just one of those functions, which is not propagating.
So remember that potential mode is just not the 0 component. There are also transverse components of the potential mode as well, right? Mm-hmm. So it's not a gauge. It's not a statement about gauge. It's a statement about the dynamics of a bound state, right? Mm-hmm. In other words, you certainly, like in QED, you could choose a gauge where A0 is equals 0 if you wanted to, right? So let's imagine we could have gone through our whole analysis with QED in the A0 equals 0 gauge. It's a little bit tougher to do technically. I mean, not hard, you could do it, but, and then you would still have AI potentials, right? So it's important not to conflate the gauge degrees of freedom as unpropagating degrees of freedom from the potential modes, which are non-physical, right? In the sense that they don't exist as asymptotic states if you're doing it in QED. they're off shell modes. So
right. Okay, yeah, thank you.
sorry, it's having problems mirroring. Okay, so I could expand this guy out. To save some time, I'm not going to write it all out, but there's terms that look like there's linear terms in H with some function of V, and then there's quadratic terms in H with some other function of V, and then there's the kinetic terms. To save time, I'm not going to write them out, but this is the mv squared plus m squared plus mv to the fourth with the right coefficients and so forth and so on. Okay, so now this h is the full h, so we're going to write this h as h plus h bar, right? And then we're going to do what we did before. We're going to write h as d3k h of k of t. We're going to do the partial Fourier transform, and then we're going to carry out the exact same program we carried out previously. So if we look at the potential mode, so L of the potential, it's going to look much like it did in the case of QED, just with different contractions. Because we have more possibilities. Okay, so as before, the time derivatives will be subleading. So this is in order v squared correction, v squared correction. The propagator, the 2-point function, will come completely from here, and will scale as 1 over k squared, just as it did in the past. So in fact, the propagator in momentum space times a tensor structure P mu nu alpha beta, which is just written in terms of, so this thing is just okay. So so now let's we can go through all our scaling arguments as we did before to read off how h of k scales as v to the 1/2, and this is in momentum space. In coordinate space, which we'll also use later, it scales also as v to the 1/2, but over r, and this guy scales as v to the 1/2 r squared. Okay, and we're going to use that to determine the scaling of the terms in the action. Okay, so I haven't, because I didn't write out the exact form of these f's, but I'm going to tell you what they are now. So if we look at v to the 0, there's a term that goes like minus m over 2m Planck h00. At order v to the 1, minus m over m Planck vi h0i. And at order v squared, I'm not going to go any higher. is minus m, because this is where the first sort of non-trivial thing shows up. Okay, so let's calculate the Newtonian potential and check our scalings. Okay, so let's look at each of these terms and see how they scale with L. So if we look at L to the, let's look at this guy here. Let's power count that term. So this guy goes like dt m over m Planck h00. Okay. So we said that m, let's collect our scaling rule for the angular momentum. Okay, so this tells us that m over m Planck scales as the square root of VL. So, and h00, this is in coordinate space, we said scales as root V over R. Okay, so this guy scales as R over V. This guy scales as V to the 1/2 over R. And this guy scales as square root of V times L. So this, the whole thing scales as, so this guy goes like R over V, square root of V L. And then square root of V over R, which goes like the square root of L. Okay? V to the 0. So this leading order term goes like V to the 0, square root of L. So let's calculate the leading order contribution to the potential. Well, that comes from two insertions, let's call this of LV0. Right? So this goes like, and then we have minus m1 over 2m Planck, minus m2 over 2m Planck, right? That's insertion of this two of these guys, sorry. One on the top line, this is m1, and this is m2. And then we have the contraction of h00. And then we have e to the I k0, t minus t prime. So let me do this in momentum space. That's the propagator for this line. Okay, and then P0 0, 0, right? Because we're contracting an h00 here and an h00 here. Okay? So this just becomes, you can just do this integral, and it becomes m1, m2 over 4m Planck squared. And then there's a, I'm not keeping track of the overall factors. And then there's a 1 over r. So as you might guess, this just gives back V is G M1 M2 over R. Okay, just as we got before. Now, so let's check the scaling. So we could try to work out the scaling here, but we don't need to because we're already done. So since each one of these insertions we said scales as the square root of V, square root of L, then this V has to scale with L, right? Because this scales as L, this scales as L. That's the point of making sure everything is homogeneous. Once we know everything is homogeneous, then we can just read off the power counting at our leisure. Okay, I think I've gone over 7 minutes. We wanted to leave time for more questions. So this might be a good place. So, I mean, I realize we're taking a giant hammer for a tiny nail. We've just rederived Newton's equations, but the very next step will be the first one where it's non-trivial.
Perfect. There's plenty of time for questions, so maybe we can start the recording now as usual.
I mean, if there are no questions, I can keep going, or if people are tired and they want to stop, then we can just continue tomorrow. Whatever the organizers want to do.
Let's wait 1 more minute to see if there are questions now. Otherwise, maybe you can do 10 more minutes if you wish.
Okay.
As you feel like.
Yeah, I'm happy to, you know, we'll get a little bit further if we can finish something today. So, but I don't want to, you know, if people have other time commitments, I don't want to.
In principle, we have time booked for this lecture. And
we had time booked for the questions anyway, right? Okay, yeah.
So it's fine. If there are no questions for the moment, take 10 more minutes, and then we do 10 more minutes of questions afterwards.
Okay. All right, sounds good.
Okay.
Okay, so that's the leading order potential. Let's calculate the order V squared corrections to Newton. Okay, well, since we already have our action up to order V squared, we can calculate with impunity now up to order V squared. So what kind of diagrams can we get? And again, when I draw these lines, what I really mean is this. This is the same thing as that. But the lines are sort of a bad habit that I've inherited from my particle physics upbringing. So we can have one insertion of LV1 on each line, right? Or I can have one insertion of LV2 and one insertion of LV0, and of course symmetric. Right? Those are all there. But in addition, we have some interesting contributions from these quadratic terms. So oh, sorry, that's why. Sorry. There's also this term here. So let's look at these contributions. And let's look at how these, so that looks a little strange because it looks like they may not scale properly with L. But before we do that, we can see that what those contributions are going to contribute. Okay, and plus symmetric. So let's power count it. So what we said was each one of these guys we know scales like root L. And so that gives us potentials that scale like L, which is good, which is what we want. Actually, say the integral dt scales like L. But what about these guys? So let's look at these terms here. So if this guy we know, these guys we know scale as root L. So it better be that this guy scales as L to the 0, otherwise we're going to get nonsense, right? So let's look at how these guys scale. So we've got dt h00 squared m over m Planck squared, for instance. That's one of the terms. The other terms will scale in the same way, right? And we said dt scales like r over v. And we said h00 in coordinate space scales as root v over r. So we get a v over r squared. Then we get an m over m Planck. And then a residual 1 over m Planck. Okay. Now we said m over m Planck. We worked out up here. So let me insert an m here, and then another m downstairs to cancel it. So now the v's cancel, and we have 1 over rm times m over m Planck squared. So this goes like 1 over rm times v times L. But let me put in a v here and a v here. And this rmv is L. So this goes like v squared. That's exactly what we would expect. This guy goes like L to the 0 v squared. And then the potential that you generate will scale as L v squared, which is exactly what we want. Okay? So calculation of these diagrams is just relatively straightforward to do. But there's one other correction that we need to include that had we not included, we would get the wrong answer. And that is a diagram that looks like this, which we call the Mercedes diagram. Okay, so this is an insertion of LV0, 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 and here we have a bulk 3 graviton vertex, okay? So let's work out the scaling of that bulk 3 graviton vertex to see if it's consistent with what we have. So this vertex is going to go like 1 over m Planck d4x, sorry, this is m Planck squared, h dh dh. Because remember, r has two derivatives in it, and we're pulling out the cubic term, so it should have 2 derivatives and 3 fields. Okay. Oh, actually, no, we got to get the units right. So I think it should be M Planck, right? So H has units of mass. So this is 1, 2, 3, 4, 5. Yeah, that's right. So one power of M Planck outside. Okay, so let's figure out the scaling. This is an excellent exercise. Now these guys were taken to be potential, so they're going to go like this, right? And so how does d4x scale? Well, d3x for potential mode, we know goes like 1 over r cubed, and dt goes like, sorry, what am I saying? Okay. So I'm just keeping the r here for units purposes. So if we're only interested in v's, then we would just have, this goes like v to the 0, and this goes like v to the -1. Okay. Now we're interested in the leading order piece here, and remember that d0 is subleading because it goes like v. So these are all going to be i's at leading order. Okay. And these h's we said scale as root v over r. So let's keep track of so this guy we're saying goes like 1 over v. This guy goes like root v over r. And we have 1, 2, 3 of them. And these derivatives each go like 1 over r because they're spatial. So if we're not interested in r's, we can always put the r's back in when we're done just on dimensional grounds, okay? So let me just write this as root v cubed, okay? So this whole thing has to be unitless. So this guy goes like r to the 4th. So if we're going to put the r's back in, and then we've got a 1 over M Planck. And an overall r, right? To make, sorry, an r downstairs to make it dimensionless. Right? So this thing is going to scale like square root of v. And then let me put in an m over M Planck. And then I've got an r m here. Okay. And let me add a v here and a v here, just so I have everything in terms of objects which I want. So now this goes like v to the 3/2 m over M Planck, 1 over L. So this is L, right? And we said that m over M Planck goes like root v root L. So we have v to the 3/2 square root of v square root of L all over L. It's like v squared over root L. But that's exactly what we need, because each one of these guys goes like root L. So this whole diagram is going to go like root L to the 3/2 v squared over root L. goes like V squared L. Okay. So we definitely need to include this. And importantly, it is not quantum mechanical, right? We can see it's not quantum mechanical because if it were, it would go like L to the 0 and not L. So that was the whole point of all the power counting. So now we're almost done. So we have, how many diagrams do we have? We have this one, this one, this one, the Mercedes diagram. And we still have one more diagram, which we should not forget, which comes from the corrections to instantaneity that we had in QED. So this is the k squared, k0 squared over k to the 4th. And the calculation of these, this diagram is very tedious because of this vertex, the tensor structure, that vertex. The easiest way to do this calculation is, well, there are ways to avoid this, which I'll discuss. But if you want to work, if you wanted to do this calculation, it's best to just do all the tensor contractions in Mathematica using X-tensor or FineCalc, whatever your preferred mode of calculation is. And the final answer looks something like this when you add up all the terms. Okay, this guy comes, this is the Mercedes diagram. You can tell because it's got another factor of G. That comes from the bulk vertex. This guy looks a lot like the piece we had. These two guys, in fact, look like the piece we had in electrodynamics. And there's one piece that looks slightly different. And I should say these are all coordinate dependent quantities. The potential is a coordinate. So as opposed to 2ED, we need to be a little bit more careful in GR because we've chosen a coordinate system. We've chosen a gauge, a harmonic gauge in this case. So I haven't, when I wrote down way back here, I neglected to mention that this is just one, I haven't told you what my gauge choice is, but the gauge fixing condition will fix the tensor structure of that propagator. So this result is a gauge dependent quantity. It shouldn't be surprising. It depends on your choice of coordinates. And in fact, there are many simpler coordinate systems you could choose. Coordinate systems, for instance, where that term is gone. The potential is not physical. It's not a gauge invariant quantity. The power at infinity is gauge invariant. So no matter what coordinate system you choose for the potential, the at infinity, whatever you calculate, the physical quantities you calculate won't depend on the gauge. And a typical physical quantity that you would measure would be the potential at infinity. So that this is just one convenient gauge to calculate. This method of calculation using Feynman diagrams is not simple. And so people have used this method to calculate up to V to the 8th. And once you get to the V to the 8th, you get like 500 Feynman diagrams. And so clearly that's not the best way to calculate. We now know nowadays, for instance, that, that using amplitude methods, if you guys are familiar with those, there's methods to calculate all the quantities in one shot without calculating individual diagrams. And it makes things incredibly simpler because you don't have to carry around there's a lot of extra gauge dependent baggage. So if you use these S matrix techniques, you can calculate all these diagrams sort of simultaneously. And there are lots of other techniques that people have developed subsequently where you can reduce the workload of having to calculate, Feynman diagrams like this. There's tricks that you can use by choosing gauges that make your life a lot easier. But those are technical issues, and I was really here interested in conveying the important aspects of building the effective theory and the physics behind it. So that's a good place to stop. I should say this potential, this is in the PN notation, just in case you guys ever read it, in post-Newtonian notation is V to the 2n is called the NPN correction. So this correction order V squared is 1 PN. And this is called the Einstein-Infeld-Hoffman potential. They were the first ones to calculate this. Actually, it's not true. It turns out Lorentz actually calculated it before then, before they did. And most people are unaware of that. In any case, that's what that potential is. And that's the 1 PN potential. People have calculated now up to 4 PN. 5 PN is the end goal for reasons which I will discuss next time. Okay, so we have a good place to stop right there.
Okay. All right, so now that we can take the questions, no? First one by Armand, please.
Yes, hello, Ira. Thank you for the lecture. So I was just curious about, so the last thing that you said, like about these methods to calculate easier the integrals, and then you mentioned S matrix formalism. I mean, did you like thought about, I don't know, like cutting through the diagrams and stuff like this, that the usual things we do, or is there maybe some other technique not known to students, but
No, so so what's interesting is you can use all the usual unitarity sewing techniques, right, to calculate these diagrams, but it's actually a little bit easier than normally because you can throw out the quantum pieces. And so a lot of the tough integrals that you have to do, you can just ignore. Because remember, when you're calculating an S matrix element, it includes all the quantum pieces. And so, when you reduce it to a set of master integrals, you can just pick out which master integrals are actually quantum mechanical and just throw them away. So it's actually a little bit easier than doing the full quantum computation. Although usually, people who are experts in this field have code that do these things and includes everything, and then they go in by hand and pick out the pieces that they want. I don't know if that answered your question.
Yeah, he says yes.
Okay.
Okay. Next one is Max.
Yeah, thank you very much